Hey, John here. Let's talk about the vector template in the standard template library. So let's start with what is the thing. It is a container, and this word means something very specific in standard template library. A container template, because they have different kinds of containers. They have lists and vectors, and they have maps and sets and stuff like that. That acts like a C array. Okay. Now, if you wanted something that acts like a C array, just use a C array. So why do we do this? Well, it has extra features like error checking and bounds checking. All right, the big win is we have bounds checking. You know, when you start poking around at things inside a C array and you access the elements off the end of it, the compiler can't help you. In this situation with a vector, it can. Of course, you have to use the bounds checking. You can certainly circumvent this if you want. But the point is, you can have bounds checking, among other things, when you use the vector template. All right, so how do you create one of these things? Well, it should come as no surprise when creating the instance of something that is a template that you use a template type of notation. Vector of integers is how I think of this, right? There's the parameter type for the template. It is a vector of integers. That's what this thing is going to do. Let's call this thing vi. Just vector of integers. Why not? So what's inside this thing if I do that? Well, the template is a manager of this C array. It does actually have a C array inside of it, or at least it behaves as if that's the case, all right? It can be implemented using anything. It doesn't really matter. As long as it behaves like a C array with this management infrastructure going around it, all right? So when you create one, what happens is it pre-allocates space to hold an array of some kind. And over the course of time, if I start adding things into this array and I overrun the end of it, again, depending on how I do it, if I use the right way, it'll automatically make it bigger for me. It can even shrink it down if I start deleting things out of there, all right? So it's this manager of this C array. Well, let's look at some terminology here. So what's the size? Just like a C array, the first element is 0, 1, 2, and 3 as you go along through n minus 1, where n is what the template library here calls the capacity of this array. In a C array, you might just think of that as the size or the length of the array, the physical size, how many elements can it have. And these are fixed. And this one, as I just mentioned, could be dynamic. So what happens is we have the notion of how many elements it could be and how many elements it has currently stored in here. So it keeps track, unlike the C array, how many elements we put into this array. Okay? So that is a notion of size, and it has a notion of capacity. Right? What are the differences? All right? This one is number of elements in the vector. I'll abbreviate because I run out of space over there. And the capacity is the size, the physical. I'm finding it hard to find a word to define capacity without using the word capacity. Capacity is the physical size. That's this. It's the n in this case, right? So this is the physical size. And the size is the logical size, right? How many elements are inside of it versus how many could it totally hold before we run off the end. That's what these two things are. And we're going to see these come up when we look at some sample code, all right? So the overall value of a vector over a regular C array is that it provides the automatic management of the size and the capacity of an array that's buried inside of this template class. So how do we use this thing? All right. Now, we can use it just like an array if we want to, but if we do that, we don't get the benefits of the bounds checking, right? So let's say I have a vector of an int, just like before, vi. What do I do? Okay, how do I use this thing? Well, I can say things like vi dot pushback, 23. This will then append the value 23 to the end of this vector. So if I create it and immediately do this, the state at this time is that the vector itself will be sitting here. There'll be a 23 in here at element number 0, and so on, right? It can have n minus 1. The current size at this time would equal 1. The capacity would equal n, right? If I do another pushback, maybe I say pushback 12. Now the size will be 2. And the capacity may have changed, right? If it had up here, if the capacity was 1 and it only had enough room for 1, and I want to add a second item, I would have to at least look like this. Okay? The capacity, if it was 1, would have to at least increase to 2. Okay? And every time this happens, so here's one of the shortcomings of this thing, right? Every time you increase the capacity, the whole array needs to be reallocated. Because according to the documentation of the vector class, it really does have a regular C array hiding inside of it. And if you ever want to put more stuff in there than can fit now, it has to create a whole new one, copy all the contents over to the new one, delete the old one, and reset all of its settings and stuff inside its your vector instance based on the new structure of this array. All right. So what's the takeaway here? Don't be wasteful in here. You can manage the capacity. If you want, you can manage the capacity of this array such that this reallocating doesn't happen very often. You can actually set this to like 1,000 and then do a bunch of pushbacks, knowing that all of them will just fill in the current array because the capacity is already there. If you don't do anything at all, it'll kind of try and figure it out for you, but it may not be as efficient because of this reallocating that I just mentioned, all right? So seed that back in the back of your mind when you're dealing with large volume. When tiny little things, it doesn't really matter. You won't even notice, okay? But if you're going to put millions of things in here, you need to think more about the difference between the size and the capacity over time. That's the takeaway here. So let's look at one more thing here before we start diving into the code. Along with size and capacity, let's say I have a vector like this. All right, let's say there's a couple of items in there, maybe a 12 and a 72 and a 23 and whatever, okay? If that's the case, let's say the size is 3, all right? So everything between here and the last one is unused. The capacity is n. Right? Size is 3 because I have 3 elements in there, okay? Now, we need to understand this thing here. Begin and end. Now notice I was careful where I put this arrow. Begin is obvious. Begin points to the first element. Or more accurately, I'll say it's the first element's location. I'll put quotes around that, okay? Because it really means, where is it? I represent the location of the first element. If this was a C array, for example, begin would be the value of a pointer whose contents is the address of that first element, which would be this element number 0, right? right? What would end be in this scenario? If this was just a C array, end would be the address of the value that would be stored at 3, even though there is not one there. What does that really mean? End equals the location. Again, I'm quoting this, right? Because there's nothing there where, you know, the next element would go if you added another one to your array. If you did another pushback at this point, what would happen? It would push it into this location and it would move end over to there. So this is the, you know, it's kind of, you know, it's the last location, oops, you know, would go. So it's the last, it's the location of the last thing in the vector plus 1. Okay? This off by 1 concept here is called an open-ended range. And this is important to understand, okay? Because in the standard template library, there are functions that are provided, all of which expect an open-ended range in their parameters, okay? So this notion of this begin and this end, the end off by 1, this can be confusing. So I want to really punch this, right? So what would happen here? It allows us to write functions that kind of work like this. For, now I'm going to abbreviate a lot here, like maybe IT, and this is an abbreviation is very commonly used for variables that are called iterators, and we'll talk all about that in a few minutes. Would be like, you know, blah, 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 begin. Okay. And then while IT is not equal to end, right? And then you would say plus plus IT. Look at this for loop. Again, if this was just a C array, you could do quite very much the same thing. You could have a pointer that points to the first element in the array, and you could have a pointer that points to one past the last element in the array, and you could write a for loop exactly like this and say start with a pointer here, and until the pointer equals this guy over there, do something like print it out, you know, like, you know, C out, whatever, and go get the element in the vector that is represented at the position that this variable here that I'm calling IT represents, okay? So this here is key. This is where we get all the reuse from the standard template library, at least where containers are concerned. You're going to see this theme come up over and over and over again. Open-ended range is your friend. You can ask, why didn't they just put end to the last one? It has to do with the pros and cons of different types of containers like linked lists and things like that that behave very differently than a simple array, all right? The vector, simple array, trivial example. So some of this stuff is going to be really gratuitous right now. But by standardizing on this way of thinking with these open-ended ranges, we get a huge benefit because all the other ones will behave the same way. For example, all right, let's say I have a vector that has a bunch of elements in it. N minus 1, and we 0, 1, 2, dot, dot, dot. And we have our nice begin here. We have a nice end. These little dots, I'll show you this notation in a minute, why I'm doing that. It points in here somewhere. So as drawn, I don't know how many elements it has. It doesn't really matter, right? But the end over here points somewhere over there, all right? What can I do with this? I can call a standard template function to sort the element. Let's say this is full of a bunch of random values, okay, and I want to sort them in ascending order. Well, there's a standard template library function called sort that takes these open-ended ranges. It makes sense. Why not, right? I don't want to write my own sort routine every time I want to sort something. Use a standard one from this library. And here's how it works. So let's say I'm not going to put the definition in here again. We have our vi vector from the last example, right? I can call sort, and with nothing more than vi.begin, comma, vi.end. Done. This open-ended range that says the elements are between these two things. These things are called iterators, and again, we'll get back to those in a minute. From the beginning to the ending, I want you to sort this in ascending order. Done. Okay, that's a lot easier than writing your own, whatever, selection sort or something like that, and spending all your time debugging that. So we don't have to write sort routines anymore. We just call this. All right, let's look at some code. All right, so here's our example program, the usual boilerplate stuff up here. Include the stuff you need to include, bring in the namespace so we can use short names for those items there. What do we got here? What's new about this? Maybe a constant expression if you've never seen one of these before. This is better than, for example, you could use like a pound define if you wanted to. And maybe I wrote, num elements like this, and I would put 10 in here. The problem with this is that there's no scope on a pound define. It'll go everywhere. Now, in this particular example, this is of global scope anyway, but point is the pound define is a text based substitution that has no real meaning. It has no data type or anything. This is the character 1 and a 0 that this so-called macro name represents, right? So it has no data type and it has no scope. A const expr, on the other hand, I could put these, for example, inside main, and now they're like a variable, but they're not variable because they're constants, right? And a constant expression means that the compiler will deal with these values during the compilation of the program rather than when the thing runs, as is the case with either a const or a regular old variable, okay? So the scope of these now is inside the main function. They don't bleed out into the rest of the file here, okay? Now, because there is no rest of the file, and I do mean them to be global in this particular case, I'm going to put them up here. I just wanted you to see these because this is what, modern programming is doing rather than using macros for those items that really have a data type. All right, in this case these are integers, right? All right, just want you to make sure you understood what that was if it's new. All right, so inside of main we're going to create an instance of vector that contains integer elements, okay, and I'm going to call it vi. Now what we say is the vector itself is an abstract data type. Okay, that might be new to you as well. Vector itself is abstract. It's not until I give it, a thing to put in there that it becomes realistic. So it's an abstract data type that we can use to contain things, in this case, integers. You can put anything you want in there. You can put strings in there. You can even put another vector in there and create a two-dimensional vector if you wanted to, all right? Let's keep it simple for the first example. Just put some integers in there. What are we going to do? Let's say we want to put 10 in there. This is the pushback function. Now, you can look up things like this and how this all works by going to websites like this c++.com, right? So I went over there, I opened up the containers link in this little menu and clicked on vector, and that's what I'm at over here. Let's zoom in, because I can't really read the text if I don't do this. It's too small for my old eyes. Okay, here we go. Look, it's a template. It looks like this. You can give it, this is the type, right? And it's called vector, and it will create a new class for you of that type. So let's look around and down here. These are then, of course, all the things you can do with a vector, all right? So one of the things you can do is call pushback. If we click on here, it says, here's what pushback does, okay? It adds a new element to the end of the container, all right? And if there's not enough room, it will reallocate the space, like I just said earlier, right? So what happens is it effectively increases the size of the container size by 1 because we added a new thing to it, all right? And yes, it could increase the capacity as needed as well. This site's kind of nice. It has a bunch of little example programs in here as well, just like the one I'm writing here. Okay, so let's go ahead and look at the rest of this. So what am I doing in here? I'm going to go from 0 while less the number of elements. That means I will add a total of 10. And their values will be the same as their index numbers. Okay, right? Because I'm going to go from 0 through 9, because this is less than. And I'm going to push all the values, 0 through 9, in as elements in that order. And then I'm down here, I'm going to go from 0 to 9 again. And I'm going to just call it this at function, and I'm going to print them out. Okay? Now, the at, of course, is the an accessor method in here. We go back to here and we look it up. And it says, I want to access this element. And so does the square bracket. We'll look at that in a second. The difference between the and the square bracket is that this thing checks that it's inbound and valid. Okay, if we go back and look at the square brackets, it says it won't check. And it'll just give you what is supposed to be. Similar to and is the same behavior, except the is bound checked and equals, blah, 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 and it'll throw an exception. We can talk about exceptions later, and that's a discussion for a different time. And of course, the square bracket version does not do this bounds checking, okay? Why do they have both? Well, if I use the square brackets and I don't do bounds checking, this code will run faster. But the risk, of course, is if I'm not perfect, I got to have a bug in my program. For now, I'm going to just use the one here, okay? It turns out this program is so locked in. It absolutely must have 10 because I just put them in there. And therefore, I could use the square brackets down here as well. All right, so let's go ahead and compile this up. It looks like it's already compiled, right? I got a bunch of little test programs in here. Let's run it. This is the one we were just editing. And it prints out 0 through 9, exactly as we expected it would, right? Fill it in with the values 0 through 9, go through them all one at a time, print them out. Yay, we've just reinvented the C array. Who cares, right? Well, let's look at this other one here. This is where it starts getting more interesting. The usual boilerplate on the top of my constant expressions for things like this. What do we got now? I can initialize my vector and fill it up with a bunch of elements already. So num elements here is 10. What this is going to be used for is it'll set the initial size, which is kind of, think about that for a minute, right? What does that really mean? And wouldn't it be better to set the initial capacity? I don't know. I didn't design this. They chose to make it set the initial size, which, in turn has to then also set the initial capacity to at least big enough to hold the size number of elements. So I can then print these things out. I can go reach in there and grab it. What's the size? What's the capacity? I don't even know what the capacity will be. It depends on how it was implemented. Probably also depends on the size that I put in here. I mean, yes, it does. However, what I meant there was that it might actually make the capacity bigger than size so that if it grows, it doesn't have to reallocate it right away. Okay? Now, back to this whole notion of size versus capacity, and why does anybody even care? Well, you care because if we set the size to 10, that means that we actually have placed 10 elements in this array. Well, what are their values? These values, if this was a C++ class that we created, would all have to be constructed. And the constructors that are used would be the default constructors for whatever the thing is in here. Now, if it's a native data type like an int or a float, the template will just set all the values to 0. Okay, so we'll see that in here, right? So what are we going to do? We're going to say just put 10 elements in this array, or rather vector, I should have said. I'm going to print out the size and capacity, and then I'm going to go in there and I'm going to go through them one at a time, and I'm going to print them all out. So if I say, well, I is less than the size, which is the total number of elements in there, which is 10, and I want to access them by 0 through 9, right? And then I add 1 to my little index, and I can go ahead and print them out just like I do if I wanted to use like in a C array. Again, I could have used vi.at and put I in parentheses like we just saw, right? Well, what am I going to do then? I'm going to come down here and I'm going to change the value. So what I'm going to do is I'm going to say vi sub I equals some other value. All right, I'm going to just set it to I times 10 at this time. All right, I'll go then in here, and I'm going to print them out again. And I put little comments in here so we can follow along to say, well, which one is this? All right, so after I've replaced the values of the first 5 elements, I'm going to print it out again. Then what am I going to do? I'm going to say, that's the printing. Then I'm going to go on and do some other playing around some more. I'm going to add a whole bunch more elements. And we're going to play around with this as we go. So let's just look at the first part of this thing and come back to the rest. Let's just fill it in. Make sure we all follow along what's going on up here before we get to all the fancy schmancy stuff down below. So that's this vec2 example program, all right? So let's look at the fancy schmancy. Whoa, lots of stuff going on in there. Let's run it again. Save some space here. So what do we do? First thing it does is creates the 10 elements, right? So we can see it doesn't have to make the capacity equal to the size, but in this case, it simply does. It initialized all those integers to zeros, okay? That's the printing that happens right here, all right? Then we're going to replace those first 5 values, and then we're going to print it out again right there, okay? So here's the note about I've just replaced the first 5 values, and we print it out again. We print out the size, the capacity, and we print the new values out. Great. Well, what happens? This is element 0. I times whatever it was, 10, is 0, and 1 times 10, 2 times 10, and so on. So these are the first 5 elements have been rewritten. It's just coincidental that the first one is the same value it had before, okay? Now let's look down here. What's this reserve, resize, and all this other stuff? Let's leave this alone for now. These are commented out. What would happen if I push back a bazillion new elements, or in this case, 20 million, right? I'm going to just keep calling pushback for now. These other ones are commented out. We'll come back and see what happens if I do that in a minute. What happens? Well, after I added the bazillion, I'm going to reprint out all this stuff. And while I'm at it, I'm also going to call the front and back accessors, right? Let's go back to c++.com and look at what the heck does front and back do. Front returns, or more accurately, they say it accesses the first element. Well, what I think of this as doing is returning the value of the first element, all right? So if you come in here and it says I'm returning a reference to the first element, you know, the semantics of how it does it, right? So it will return the value of the first thing. So in their little example code, if you push a 78 and a 16 and you say, well, that's the front one, oh, they're actually getting cute and subtracting. They're convoluting their example. Let's look at this other example. What I'm going to do is grab the front and back value and just print them out without playing any games, okay? Well, what should the front and back value be after we've added these bazillion items, right? Well, notice I'm going from 10 to 20 million for the element numbers here. The first 10 we just saw, okay? The first 10 are this right here at this time. We're going to now add up to 1999999, right, for the element numbers. And I'm going to poke all those in there. So the first one, the front, is going to still be 0. The back will be the last one that I just pushed in here, which will be this 1999999 and so on, right? So let's look and see what we got. Add a bazillion elements, and afterwards the size is a bazillion. You'll notice that it decided that we were poking a lot of stuff into that array, so it started reserving extra capacity for performance reasons. It doesn't just do it one at a time and keep making those copies. It allocates, you know, chunks, and that way I can put another 970,000 things in there before it has to do it again. That's kind of nice, but of course all this extra memory is being wasted, okay? Almost a million extra elements worth of capacity is in there, all right? We'll come back to that in a little while. The front element value is 0, the back element value, the last one that is there is the 19999, just like I saw, all right? Now let's look at some of the other things that are going on here. We get the front, the back, the push back. What else is going on here? Well, I can set the reserve myself if I want to. I can even resize it. What's the difference? Well, the reserve is this changes the capacity. All right, if I just simply set it up to 20 million, I'm saving myself time when my program runs. So you might want to do that if you're going to go into a loop like this, so it doesn't have to kind of try and figure out how to keep increasing the capacity and keep making all those copies of that array, okay? This I can also do too, but remember, this changes the size, which means it'll construct new elements. And if I'm going to just make room so that I can add new elements down here, I don't want to construct 20 million new elements, or 20 million minus 10 in this particular case, roughly speaking, 20 million elements, and construct them all and initialize them all, only to immediately throw them away by replacing them with new values. This would be the sign of the new guy that just joined the team and doesn't know that he should have done it like this, okay? So notice the difference. This one says, reserve the room, but don't put anything in there. I'm not constructing. I'm not wasting any CPU time doing that. It's just simply a one-shot, make a giant array that's full of garbage, okay? This one is make the giant array full of garbage and reset it and clear it all out. This one will take longer. It won't be a huge deal because I have integers in this particular case. But let's say this is a vector of strings. It takes a lot longer to initialize an empty string than it does to just set an integer to 0, is my point. This can waste a lot of CPU time, all right? Now, these are commented out. We can come back and play around with them. Let's go down here and play around with this first. Remember, I can use the square brackets and I can use the parentheses and things like this to set these values using the index number like an array. And this one is the same thing with bounds checking. So what do we expect is going to happen here? So let's take the pushback out, right? The pushback is, it will allocate space and set a value. Allocate space, I should say, if needed. Oops. Let's change the word space to capacity, because that's really what it's doing, if needed, and sets the value of that element. All right, so this is doing a lot of work. You use this if, I'm the new guy and I don't realize, I want to make sure everything is error checked, okay? I don't want to make fun of the new guy. You should do this as a general rule if you really need to put something at the end. That way it'll get there. You don't overwrite the end of the array. You don't have any problems. You didn't screw anything up. This is guaranteed to work unless your machine runs out of memory physically. This one here will do a similar sort of thing. It'll check. This one this one is based on the current size. If I less than size, then this is okay. All right, think about what I just put in there. This is not based on the capacity. This is based on the size. This allows you to replace the value of something that's already there. If I wanted to do this, I would have had to have first done this, in other words. Okay, let's go ahead and compile and run this. I just remove the pushback, and I'm going to just put this in there. Let's see what happens. Okay. It croaked, as we would expect. Why? Why? What does it say? Terminate called after throwing an instance of out of range. And what is going on here? I got a vector that was doing a range check on something. It's currently 10, and this, which is greater than or equal to the size of the vector, which is 10. So it died, and it says it dumped core, and you can open up the debugger and figure out what's going on in there. It would have been nice if they told me the line number in the program where this error came from, because on a giant code, like a 100,000 line program, it'd be nice to know where that is. If you don't know, you can use the core file and you can use GDB and all that other stuff. Totally subject of a different lecture. Let's go back and look at our code, because I know where it is. I created this error. We only changed one line of code, and therefore that must be the line that's croaked, okay? In this if expression here, I wasn't lying to you. This thing checked. Okay, and that's what it does if your check fails. It throws an exception. That's a discussion for another video as well, another time, if you don't know what those are. The point is, your program died right here and immediately when it did something wrong. Rather than, if I do this, let's see what happens now. Remember, the square brackets do not do this bounds checking. This one did not increase the size to make room for it like this guy down here did. So what do we got here? This one will actually increase the size and allocate the capacity and do everything is needed to get that new value into this vector. This one here doesn't help you a lot, but at least it checks first and it stops your program if you did something like used a value that's too big and you're not using this in this scenario to replace an existing element. This one checks nothing whatsoever, and it works just like a C array, and it just assumes you know what you're doing, and it'll poke it in memory wherever this thing represents. And because I'm going to do 20 million, right? And we know what the size and the capacity was up here. We know it's not 20 billion. All right, it's going to croak. Okay, let's go ahead and compile this thing up. Clear up some space here. Oops, let's run it. vec02, right? So this one now, we got a seg fault. It doesn't even help us. It just says, no, I'm not running anymore. You suck. Your program died, right? Why? Because up here, when we replaced the first 5 elements, remember, the size was 10 and the capacity is 10. So when this thing died in the scenario that I created here, we know that the size of the capacity that is printed out up here is still 10. So I said vi sub 10 equals I. I just wrote 1 past the end of the capacity of this vector. I'm corrupting memory. And certainly between there and by the time I do that 20 million times, I'm writing all over the place. Of course, the program's going to croak. Okay, so let's see what happens if I resize it first. Let's go ahead and turn on all these after reserve / resize. So we know what's going on here, right? If I resize it, I will create it and I will initialize / construct all these new elements so that something like this can work without croaking. Okay, let's go ahead and run that and rerun the program. What happens? Here's the after the reserve resize, and I want to add a bazillion new elements. Well, now I can. I mean, duh. I set the size way up. Sure, I can do it without my program dying now, okay? And I can do it without any error checking at all right? I got my big boy pants on now, right? Where is that code? In other words, I can do this, right? Because I've taken care of what I need to do to make sure that this will not fail given this range of values up here, okay? Now, if it worked there, of course it'll work here because this is only doing bounds checking. It'll run more slowly, but just to show you, say for the sake of completion here, completeness, you'll notice, I did anyway, it may not show up in the video, it hesitated ever so slightly when it was printing this stuff out and went, yeah, and a very little pause. Why? Because it took a long time to initialize all these things, reset them all to 0, and then while I was adding the bazillion events, it took time to do all that error checking, the bounds checking, okay? Now, when we're done adding the bazillion events, notice that the front and back have the right values. We talked about that before, okay? All right, so let's go ahead and put this pushback back in here. And in doing that, what's it going to do? Now it's going to go to 40 million elements in that vector, right? Because I resized it to 20 million up here. And now I'm going to push back 20 million more. Okay, I might not want to do this up here is my point, okay? We ran it the first time, it worked fine. Why? Because it allocated the space as it went along, all right? Let's turn the resize off and look very closely while this one runs. You'll notice there's a bigger hesitation now. Again, this time it ran, it hesitated, and then it continued on. It didn't get any errors. This all makes perfect sense. The size and the capacity, we already talked about that before, okay? But it took longer to run than it did when I just simply set the size by using resize up here and using either one of these two. This one ran the fastest. This one slowed a little bit down. This one slowed a lot of it down, okay? However, let's look what happens if I change the reserve. So now it'll have the space to hold all this pushback stuff, right? Now it'll probably still hesitate a little bit, but not as much as it did before, because it won't have to continuously change the capacity while it's doing all these pushbacks. But because this is doing so much other work and checking the bounds and all this other stuff, changing the size and so on, it's still going to probably hesitate a little bit when it runs here. Okay, let me clear this out, make sure it's compiled. All right, and again, I saw it hesitate a little bit, but maybe not a little, maybe not quite as much as it did last time. So it made a little bit of a difference. It'll make a massive difference depending on the size of each of these elements, okay? The integers are small, they're easy to set up and initialize and things like that. So this is a little bit of a benefit. The benefit goes up as my point based on the complexity of the objects that you put in your vector. Okay, so let's go ahead and make sure that we all really follow along here. Now that I've changed the reserve, okay, I did not change the size. What's going to happen with these other two? This will appear to work okay, because when I'm writing off the end of this array that's inside of the vector, I know I've reserved enough space for there to be elements in there. But at the end of this, the size will not have changed, because I'm supposed to behave myself, even if there's capacity. I'm supposed to behave myself and not write into things that are not in the current size. The first size number of elements, all right? So this program won't croak like it did last time. Let me clear this out. All right, and it ran without hesitating. I don't know if that shows up in the video so much. Okay, so what did I just do? The size was 10 after the reserve and the resize, right? I did not resize it this time. I just did a reserve. Made a lot of room. I added this the 20 million elements, and that's all fine and dandy, but because I was supposed to behave myself and did not, the size is still 10. My program did not crash because there's room for all those, but they're not accounted for. The size is still 10. The front and back are 0. Why? Because the first 10 elements in that vector are these values, and the first and last ones happen to be zeros, right? Because when I added the bazillion, I did elements number 10 through, whatever, the 20 million, all the ones that would be over there, okay? And I did set them, and I did poke them into memory. That's what that code really does. It really is doing all that. But because I lied and I didn't behave myself, it's not doing what I wanted it to. This will fail also, but look at what this one does. Bang, I'm out of range, as I should be. The capacity is big enough, and I could store them in there, but the current size is only 10. So by saying I want to go over there, reach into that vector and update the value of an element at index number I, that thing has to be already constructed. It has to have a value. It's not good enough to simply have the capacity for it. It actually has to already exist in the vector, all right? So you see the difference between all these things now. I can reserve space, but those are not yet usable. That's just a matter of increasing and improving the efficiency of my code. I can resize it to create new elements. I can even create elements and give them values. I think you can put if I wanted to, I could put a 27 in here, and it would initialize them to 27 instead of 0. Okay, look it up in the C++.com or some other C++ reference website. This is not some of my favorite one. It's one of them that I go to fairly often, which is why I offer it to you guys as examples here. So where's the resize? Right here, okay? If we look at resize, you'll notice it has two different ways to call it. It's overloaded, right? I can either give it a number of elements, or I can give it a number of elements and an initialization value, all right? So that's what I'm referring to here. Okay, so let's go ahead and look at what's coming up next. Well, first of all, let's fix our program so it doesn't croak anymore. Use the pushback. and reserve the capacity. So this program now is probably what you'd like to do. All right. You can think ahead and reserve the capacity, or you can let that go. All right. We'll let it go for now. We'll use the naive approach. Why? Because pushback takes care of the capacity if it's necessary to do so. That's the safest way of all. Now, down here, it'll all make sense. We already saw that run anyway, so we don't need to review that anymore. Okay, what does it mean to resize this thing, right? Well, we did a resize up here to grow it. And if it grows it, it has to construct and initialize all those new elements. What happens? It's set to 20 million right now. What if I set it back down to 7? What's it going to do? We're going to see that what it'll do is it'll destruct all those other, 19,999,000, blah, 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 blah. All those extra elements will be destructed at index number 7 on, right? Because if I resize it to 7 elements, it's going to be elements 0 through 6, okay? So what will it do to the capacity? I don't know, but for sure, the size will go down. It depends on how it's implemented with regard to the capacity. It may or may not decide to, reallocate the entire array and free up all that extra space. I mean, I'm freeing up a lot of memory here. If I change the capacity. If I don't, that memory is still in use by this program. Now, you wonder why web browsers and big apps that are written in C++ slowly consume all the memory of your machine until the thing croaks and dies a miserable death. How come you got to reboot your machine all the time? I don't actually have that problem with the stuff I run on Linux, but other operating systems, things tend to just grow without bound forever until they die. This is why. You'll see by resizing this, even on Linux, if I'm a slob and I resize it down and don't tell it to get rid of the excess capacity, I'm still carrying around that gigantic tumor hanging on the side of this vector of integers over here. All right, so what we'll do is we're going to resize it down and we're going to print out all this stuff here. All right, let's go ahead and run that. I got another window over here. Run it again and look and see what's happening in there. Let's make sure it's compiled. Okay, so what happens here? Here's the bazillion, and that worked again because we put it back to the pushback routine, right? Then we resized it down to 7. Okay, thank you. I've just logically thrown away all the elements from number 7 through 20 million. But the capacity is still gigantic. This is that huge, tumorous, cancerous tumor that it's hanging around with all the time, okay? What are the front and back values? They're now 0 and 0 again because this is the contents of the array, rather the vector, after we've resized it back down to 7. Before we did that, of course, the back of the vector had this value, okay? Now the back is set back to 0. All right. Now, what did I do here? I resized it back up to 12 and printed it out again. You'll notice it's still carrying around all this extra capacity. Let's go back to the source and look and see what that's all about. So here I resized it down to 7. We printed it out, and we saw that the capacity remained big, but the size was down. Okay. And we only printed out the first 7 elements, and that was all fine and dandy. Let's say we then increase it again to 12. Let's go ahead and prove that, 1, 2, 3, 4, 5. I can put, a value in there. And it'll then, it'll increase it from 7 back up to 12, and it'll construct or reconstruct those elements out of that, room for that capacity. And bring the 7 back up to 12. And then after that resizing, I'm going to print all the stuff out again like we've been seeing all along, right? So let me go ahead and save this. Go back over to this other window here. Make it. So what happened here? I brought it down to 7 that we just saw before. Now I'm going to increase the size back up to 12. And of course it says, okay, the size went back up to 12. The capacity is still mongongous. And I print out the values of my vector. Now, what? Well, that's me forgetting, that when I print them out, I got the print width up here set to 3, okay? And down here, I say set W print width Oops, that's the wrong code. It's up here, right? After I resized it, and I initialize the values to this gigantic number. Okay, let's just set them all to 45, right? I would have to increase my print width to make more room, and we'll run out of room on the screen. So there's no reason to set it to a giant value. The point is the print width was 3, and I printed like a 5-digit number, so they're all going to be smushed together, all right? So that's why that happened. Let's go ahead and run it again. All righty. We reduce it down to 7 and print it out. We increased it back up to 12, and now you can clearly see the new elements that were constructed were initialized to all those 5s, or 45s, I should say, all right? Now, the next piece of code calls this shrink-to-fit function. Let's go ahead and look that up on c++.com. Here's the shrink-to-fit doc for this member function of a vector. What does it do? It requests the container reduce its capacity down to its size. Here's how you get rid of that giant tumor so that you're not wasting all this memory and carrying it around for the duration of your program that runs. If you write a program that somebody starts on their computer and lets run for a month, well, you know, you can't have a whole bunch of these vectors running around that are 99.9% unused. In fact, this is 99.9999999% unused, okay? So if I call shrink to fit, and that code is right next to after I printed it out. This is the one that we just saw. Here's the shrink to fit. Okay. Then I print out the size and capacity and dump it out again. All right. So this is the after the shrink to fit. Capacity is now 12. It is as small as it can be to service only the values that are actually in there right now. Okay, that's what this thing is for. Get rid of the excess space. Now, be careful. Don't just call this gratuitously all the time, because when you do this, it will reallocate and copy the contents of all these elements from the gigantic vector or the little C array inside the vector template to this new one. All right, my point is, you don't want to mess around with the capacity and grow it and shrink it all the time. That causes it to have to make copies of all this stuff while it goes. All right, that's where your performance losses are. Now, what happens after this bit of code? We're going to call pop back. What does that thing do? Well, we'll look up the doc in a second, but the short of it is, it's like resizing it to get rid of the last element in this vector. Okay? Oops, that's not my other window. Here it is. Let's go ahead and close some of these extra ones. So where's this pop back thing? Push back, pop back. We already know about push back. We can add a new one into the vector with that thing. Pop back allows us to remove one out of the vector, right? So it says remove the last element in the vector, effectively reducing its size by 1. Notice it says the size, not the capacity. Not necessarily the capacity. It may decide to reduce the capacity if it wants to. It depends on the implementation. So after all the other stuff that we've done, we're going to do a pop back, and then we're going to dump out size capacity and print out all the values of the vector one last time. And we can see down here, after the pop back is done, the size went from 12 down to 11. The capacity was left alone, as it didn't feel it needed to do anything. Let me put it this way. If I could resize it from 20 million and I resize it down to 7 and it didn't think that it would be a good idea to reallocate and reduce the capacity, calling, pop back and reducing it by 1, sure, it's not going to do anything. So it's not getting aggressive, in other words, about managing this capacity. Right now, it looks like it's just going to grow it when needed if I behave. And it's not shrinking it unless I ask it to by calling this shrink to fit thing here, okay? So once I do the pop back, you'll notice this has one more element in it than this down here, right? Of course it does, because the size went from 12 down to 11. All right, so this is everything you need to know about the size and the capacity of a vector and how to add and remove elements from it and how to manage the capacity over time when you're making major changes like we were playing around up here, okay? Now, What about these open-ended ranges and these iterators and things? Well, let's have a look-see at those. The usual boilerplate stuff on top, the number of elements 10, print with 3. We've seen that already. Okay, I'm going to create an empty vector of integers. What am I going to do? I'm going to put 5 elements in there this time. Oh, I'm not. I'm putting in the number of elements, putting in the same number of elements, the 10 elements, but I'm going to start them. Their values are going to be 5, 6, 7, 8, 9, 10, and so on, right? So I'm going to use pushback. I'm going to just say, here's a new value. Put this value in there, and it'll start at 5, rather than starting at 0, okay? And actually, the reason I did this is so that the front element doesn't have the value 0 anymore. That will confuse us. If the element values have the same values as the index numbers, sometimes that can be confusing. And in this example, in these examples down here, I think this is more useful, all right? So we're going to start at 5 instead of 0. After filling it in, I'm going to print it out. Then I'm going to use one of these iterator thingies, the begin and the end. So let's start at the beginning here and run this. All right, so what am I on? This is vector 3, example number 3. Oops. Now let's go ahead and make sure it's compiled. Let's make sure everything's compiled and run this vector 3 example. What does this thing do? After filling the initial values, capacity is 16 and the size is 10. So while we were poking it along in there, it decided, oh, he's keeping adding. So I'm going to add, keep a little extra capacity. Again, it's its prerogative to do so, okay? So what happens? I'm going to print them in what I call forward order. 5, 6, 7, 8, 9, 10, 11. This makes sense because that's what we filled it in with, right? Now, what's all this crap about in here? The other time I used the size and it was all simple. I just counted with a regular integer. Well, it's like I said earlier, if we learn how to use these iterators, then we can use this exact same code on any container, or shall I say any container that provides iterators, okay? Some of the containers don't provide as many services as others, right? They can only do what is possible, right? Well, just about all of them will let you do this. Iterate in order from the beginning to the end, all right? How does this work? This data type here is this cockamamie crazy thing, and we'll see how to get rid of having to type that in a minute. This is an iterator of a vector of integers. Okay, this technically is what this data type is for this variable called it. And you'll see it is kind of like the de facto default name that most people use for their iterators. It's sort of like saying I and J when you create a regular for loop like this. And everyone uses these, right? And if you don't know, that goes back to Fortran, because I and J and K and L, though any variable that starts with those letters are known to be integers, all right? Now, a little historic, ancient history there. But honestly, that's, I believe, why everyone still uses those letters to this very day. Down here, everybody uses IT, short for iterator, okay? When you're looking around on the internet for code samples and things, you're going to see this. Very common. Okay, so I'm going to have a thing that is an iterator suitable for vectors of integers. And I'm going to say I want the value of that iterator to represent the position of the beginning. Okay? And I want to say until it equals the value at the end of the vector. Do, this is a for loop. Start here until this happens over here. Do the body of the for loop, and at the end of the for loop, add 1 to the iterator. So again, like I said, this is acting a lot like a pointer, sort of. Okay, in this trivial example, it really does look like a pointer, even to this extent that where you put star IT in there. So let's make sure we understand what this is doing. Start at the beginning. While it's not equal to the end, which is the place, it's the location of the first non-existent value in this container. Okay, I don't say it is the 0th element, and while it is less than this end, I say, well, it's not equal to the end. And the reason you do this is because some containers you cannot put less thans and greater thans like you can with pointers. All right, this idiom is the de facto standard for iterating across all the positions of a container. Okay, so start at the beginning. Well, it's not equal to having gone past the end. Add 1, and and so on. All right, that's what that means. That's how I think about it. All right. Now, what am I doing in this loop? I'm going to say print to the standard output. The usual. Whatever 3-character *it. That's going to dereference this iterator. Much like it would work in a C array, like you would dereference a pointer to an element in an array, okay? So what happened when we said print them out in order? Print them out in order, well, it did exactly what we thought it would do. It's going to print them out, all the values in order, from the beginning of the vector to the very last element in the vector, all right? This loop ends because it went one past the end, or shall I say one past the last element, and is pointing now at this end thing that I beat to death when we were doing the hand-drawn diagrams, okay? Well, it's not equal to the value of an iterator that points too far. That's how you do this. Okay, now, they provide iterators and reverse iterators. Remember this begin, just like begin. If we go back over to c++.com, close the extra windows, and we look inside here, allocator, blah, 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 blah. Okay, here are iterators. There's the begin and the end. We just saw those. Give me an iterator that represents the first element in the array. This one says, give me an iterator that represents the position past the last element. Begin says, show me the reverse iterator, the beginning of the reverse beginning, they call that. All right, so let's go ahead and look at the doc here. Reverse begin, it points to the last element in the vector, i.e., it's reverse beginning. Now, what you got to keep in mind, and we'll see this in the code, a reverse iterator runs backwards. So by adding 1 to a reverse iterator, it moves from the end towards the beginning. All right, now this might seem kind of crazy, but as you move forward with the template library, you're going to find this idiom, this idea that you want to say, use the value of an iterator and then use this to move it to the next one, whatever context you might be working in. That's what you want it to do. Notice this. I say I want a reverse iterator from the reverse beginning, and while it's not equal to the reverse ending, it's exactly the same kind of thing here. Even this adding, the fact that I can add to it to move it from the beginning to the ending, all right, even though it's going backwards. Don't subtract here is my point, okay? Because it operates in backwards order. All right. And then once I'm inside this loop, I'm doing the same thing. Go ahead and print it out and use the dereference the iterator and point it out. So if you look at the output there, reverse order, now it's all backwards. Perfect. So if I want to print the contents forward or backwards, I have a way to do that. Okay. You might argue, again, why am I dealing with all this crap when I could just use, an integer and use the @ axis or even the square brackets? Well, you can in this super simple case. You can't in more complicated containers. So again, this is trivial, and it's very gratuitous to be doing all this on a stinking little vector, okay? But the beauty of this is it's easy to understand, even though it's crazy. And it's easy to apply the exact same thing to more complicated containers. So let's go on and simplify this thing. Now, in recent years, and by that I mean in the last 2 decades or so, we can now use auto. These giant ugly things. Look, I don't want to have to type that in every time. It uses the whole screen. I got to look at this thing for a whopping 2 seconds and think about it in order to try and understand what the heck the programmer had in mind, what's going on here, all right? If I just say auto on my variable, the only difference between this loop here and this one down here is I threw all this crud away. Actually, I'm lying to you. This loop up here and this one down here is that I replaced all this crud with the word auto, and everything else is the same. I think of this as like the Captain Picard type of thing, right? When he manages his crew, he just says, make it so. I don't know what this is supposed to be. I don't care. I'm a programmer. I'm lazy. I don't want to type in all this junk and then have to debug it when the compiler doesn't want to deal with it. The pain in the butt. Why? It knows full well what this function here, the method begin, returns when I call this on a vector. Why do I have to type all that crud in? Giant pain in the butt. Make it so this variable here is whatever it needs to be to satisfy taking the value that came from this method. Don't waste my time looking up how to define this, because trust me, if you had a two-dimensional vector of vectors of some complicated class, this thing is enormous, okay? I don't care, don't want to know, just make it so, all right? And just have it so that it just works. That's what this is going to do. Now, the compiler can only be as smart as the compiler can be. As long as this thing has a known and obvious and clear type, this will work fine. I mean, you might think, oh, I'll just use auto everywhere. Try it sometime. You'll find out real quick you can't do that. Okay, so what is going on here? I'm going to say make it represent the position of the beginning, the first element, while it's not past the end, add one, the usual thing. I can also do it with the backwards, and this is the beauty. Auto, IT, whatever it is, whether it's a iterator or a reverse iterator or whatever it is, apples and oranges and pears, whatever it is, make it so, and I can now iterate backwards, all right? I ran this program already, and I can go forward and backwards with auto. It makes perfect sense that it gives you the exact same thing in here because the code has the exact same meaning, right? The compiler just got the information about what the type is of this variable by looking at what this thing returns rather than forcing me to type it in again. All right, so what are we going to do? We can use a range-based for loop. This was introduced very recently, in my opinion, less than 10 years ago. They modified the language so I can even do this. What does this do? Now, we'll come back and visit this later on. This is a subject of a different lecture. However, notice the difference between all this cruft and this thing right here. What's going on with this? Well, this pattern is incredibly common. Start at the beginning, well, it's not equal to the end, add one, and then go through this loop so that I can, use each one of the values one at a time for some reason. What does this do? It does the exact same thing as this forward iterator up here. Auto. Now notice that's not an iterator, it's the value. What this thing does is it says, take this variable called I, set its type to whatever it needs to be, and create a loop such that all the elements from this container are put into this variable one at a time, and for each one, execute this body of this loop. You kind of think of it, for each element in this container, take them out in order, one at a time, store it in this variable, and then do this. Notice my point is this is not an iterator. It's the value from the iterator each time this loop goes round and round and round. So this, again, we're shortening it. You'll see this in more modern code floating around on the internet. I just wanted you to see this notation. This is exactly the same as a forward iterator set up like this up here. Okay, we'll get back to this in a lecture for another time. So what's the point here? This thing is going to go ahead and print it out in order ascending again. So here's the automatic forward and backward. Here's the range-based for loop in forward order. It comes as no shock that it is printed out in forward order because that's what that's supposed to do. Okay. Now what happens? So depending on the type of the container, we can even go forward and backward at will. All right. So let's move around. What does this thing do? Well, we go give me an iterator that's set to the beginning of this. The first element in our template, right? Our vector container. And then I'm going to go from 0 to 3 in some counter, and I'm going to say, look what's going on here. I'm going to add one to the iterator over here. I mean, that makes sense. If you can add it in your for loop up here like this, who cares? I can add it in anyway. I can use it, again, a lot like a pointer. So what I can do, I could say, give me the value, and I can print it out. And when I'm done with that, I can add one to this iterator to point to the next one. So what's this thing going to do? It's going to go from 0 to 3. So it's going to print out 3 elements. And after each time it prints, it's going to add one to the pointer here. The iterator, I should say. And then I'm going to print 3 more. And after I print those, I'm going to subtract 1 from this iterator. Right? So what's going on down here? This is great quiz fodder, okay? Let's look at this random output that's right here. 5, 6, 7, 8, 6, 7, 6. So you can see it went forward and backwards, right? Because if we print them all out in forward order, here we have them all, right? Well, this is kind of confusing. I went 5, 6, 7, 8, and then I went 7, 6. And yet my program says I want to print 3 up and 3 back down. How come it's wrong? This has nothing to do with containers and iterators. It has everything to do with the post increment operator and the fact that I printed all these first 3 out, and after I printed them out, I incremented this iterator. So the first time through this loop, it prints the value where this thing was left pointing at, which was the 4th one. Then it subtracts. If I pre-decremented it in this loop, it would do a different pattern. All right, this is a subject for different stuff. This is basics, okay? But this is trickery. So be careful. This is a post-increment operator. You should have gotten this sort of thing, 2 semesters ago. But it applies to everything, right? Pre and post increment and pre and post decrement. You got to be careful what order you're doing these things. Okay, let's go ahead and use it like a pointer. Again, I mean, this is, simple, standard pointer type things. And again, an iterator can act a lot like a pointer. So what is this one going to do? It's going to say, point the iterator at the first element that's in the container, and I'm going to take 3 of those 0 through 2 and print them out like this. I'm not going to change the value of the iterator. I'm going to treat it like a pointer, and I'm going to do math on it. I'm going to add 1 to that iterator and then go get the value from there. My point is, this is how iterators can be used in a lot of contexts, all right? So if we use it like a pointer, we can see clearly it did 5, 6, 7. That worked again, all right? Now, this not here. Let's be very careful, all right? These are not pointers, and they don't work exactly like pointers. They don't always give you what you think, all right? So, little Dante wants, abandon all hope, ye who enter here. So, what am I doing here? I'm showing you how to screw up, all right? So, big news flash. Hopefully you can see this if you're watching very quickly and setting your speed to 2 or something while watching this video. This is an example of badness, okay? This will do undefined things and or just crash, okay? So we have iterators and we have reverse iterators, all right? So what you might be thinking, why can't I just start at the end and go back to the beginning? Why can't I just reverse them? The short of it is, the end is not pointing at a value. It's pointing at a value that doesn't exist. It is illegal to set an iterator to the end and then go and dereference it like this. All right? This is illegal. All right? So we're going to run this program, and we're going to see what happens when you do this. So let's look closely. This is a naive attempt at going backwards. Start at the end, and while it's not equal to the beginning, just subtract it. Okay? It turns out that this part of the code will work for some containers that provide iterators that you can use that you can subtract. Okay, some you will see it's a subject for another time. Sometimes iterators cannot run backwards. Is the point here? But this one can, and this will actually run. But the problem is we're dereferencing the end, which is not an element that has a value. So what really happened when I did that, right? So here it is running. What did it do? Well, again, the size was 10 as it has been since we left it all long up there. It has a capacity of 16 like it was from the beginning, okay? And what's going on here? We got two things that leap right out at us. First of all, it's illegal to dereference the end because we know there's nothing there. Yet, it didn't crash my program. I got lucky. It could easily crash your program if you do something like that, okay? Then when I subtract 1, remember the end, when the iterator equals the end, if I subtract 1 of it, then it actually does represent the location where the last element is in there. So this actually makes sense. This is illegal, and I got lucky. It ran. It just happened to print a 0. Could have printed anything. When I subtract 1, it's pointing to the last element that has a value. And as I subtract and subtract, this is great. It works perfectly. But what's going on here? Well, remember how the loop works. Well, it is not equal to the begin. Remember, the begin points at a real element. An end points at an element that does not exist. So it stops when it equals begin before it has a chance to print that one out. All right, so maybe we can do something like this, right? Yeah, you can. I could recompile this and run this right now. Let's see what happens. This fixes one of your two problems, but it only fixes it when you have an iterator that can actually go backwards, right? So here's the random and use it like a pointer and then go to backwards and so on. End minus 1 does equal 14 for those containers that you can subtract a value from the iterator. Okay, so it started in the right place. It still ends in the wrong place. All right, well, what do we do about that? Well, maybe we want to go, how do you fix this one? It turns out you can't. Right? How can I say, I could change it to equals begin, but that, that won't work. I mean, it just breaks the logic. All right, so this is just all broken. All right, I'm going to put it back the way it was and leave it broken. Now, you might think, well, maybe if I shrink it to fit, that'll help. Okay. All right, let's save this, compile it up, because I modified the code there. Let me run it again. What happens? So if I shrink it to fit, I don't have these extra, like maybe you're thinking, oh, it has to do with the fact that there's extra capacity, and there really is a place for that extra thing at the end, right? Well, if I shrink it to fit and get rid of that extra capacity, it still fails. Not only that, it failed in a different way. Since I shrank it to fit, the capacity that it had, this one up here did have a little hole in there, right? Because there's a space for all those extra elements. And having the end point into that unused capacity happened to have a 0 sitting there. Now I shrank it down, it happens to have an 81 in there. I didn't put that there. I'm dereferencing the end pointer, which is illegal. That's why these are all broken and defective. So don't do this is the takeaway on this sort of thing here. All right. So this is probably a whole lot more than you would like to know about iterators right now. The short of it is these simple examples up here, like a range-based for loop, is very handy until you get heavily into all this stuff. You can just use these generic things. All right. I would use this one here to iterate forward, or I would use a range-based for loop like this one down here, okay? I have a tendency to do this because the bulk of my C++ code that I wrote in my life, I wrote all before we had the ability to use range-based for loops, okay? So if I actually look at any of my code, in fact, I don't even have auto in a lot of my code. I had to write them like this and put all the formal definitions in there of all these iterators. So I have moved on to this for a lot of that old code because I didn't want to have to redesign it and restructure it as I went, as would be the case if I did it like this, right? Because by simply changing the long name to auto to get rid of all this means that the body of this for loop still uses the dereferencing notation on the iterator rather than this, which completely changes the semantics of the body of the for loop by not having the iterator of accessing available to you. You actually have the values from the array. This would require me to have changed all the code in the body of my loops, as well as just or just the loop itself. I'm just saying. All right. So you can use any one of these methods. I prefer either this one here or this one down here. All right. Me and everyone else on the planet. Right. That's why they added the auto, and that's why they added the range-based for loops. So this is probably more than you'd ever want to know about vectors and iterators. Thanks for watching. See you next time.